In Lab 2, we'll be looking at an example and analyzing the physics of the motion of a falling object. Let's start by going over some of the fundamental principles in play. Much like in the last lab when looking at constant velocity, the fundamental principle we will be using is Newton's second law, F net equals mass times acceleration, which when rewritten for final velocity produces the equation seen here. The difference between the motion of a falling object and an object at constant velocity is the net force. So let's look at the forces that will be acting on the object when it is falling. There are two major forces in play. The force of gravity, represented by the equation, once again, F equals ma. In this case, a is the acceleration of gravity, which is 9.8 meters per second. The only other force acting on the ball that to be accounted for is the drag force. Drag force is represented by the equation negative bv, where b is the drag constant. This can be calculated based on object's characteristics such as surface area, but in our model we were able to find b using trial and error given the known amount of time and final position from our video found using Tracker. So that being said, why don't we take a look at the video being used to create our model. Now when put in Tracker, we can use the program to track the motion of the ball across that time interval, and you may notice that here in the graph relating the time to y position, it is not a linear relationship as was seen in Lab 1 with an object at constant velocity. The only instance in which this ball would be at constant velocity would be if the net force on the ball was 0. That is only possible if the drag force is equal to the force of gravity. The constant velocity at which would then be achieved is known as the object's terminal velocity. Using the information from Tracker, we can then create a Python model to simulate the same motion under ideal conditions. Some information that needed to be recorded was the ball's mass, the initial position from the Tracker video, the initial velocity, which in this case is starting from rest, therefore has an initial velocity of 0. So some of the bigger changes that occurred in this code compared to the object at constant velocity. The net force is the sum of the force of gravity represented by W and the drag force represented by Fd. You can see the force of gravity is the ball's mass multiplied by the acceleration of gravity, which is 9.8, multiplied by j hat, which indicates the direction. In this case, the object is moving along the y-axis, and the drag force is represented by the equation shown, the squares of the ball's velocity multiplied by the drag constant. This is the equation used to calculate turbulent drag. So when this simulation is run, you will see a sample graph is produced as well as a simulation of the ball with the different forces acting on it, the length of which arrows indicating the magnitude of the forces. When placed in a spreadsheet program, the data from the Python model can then be plotted alongside the experimentally obtained data, and you can see that the model very closely represented the actual motion of the object. Another Python model was then created excluding the drag force, only accounting for the force of gravity, and you can see a pretty notable difference between the slopes of the two, as the model without drag has a marginally steeper slope than that of the model with drag. This is because the velocities of the two as represented by the slopes of the graphs is the magnitude of velocity is higher for the object when there is no drag accounted for. Another condition that could be accounted for would be if the object was initially thrown down, thus it had an initial velocity. So we're going to look at an example of that, a model of that. As you can see in that brief animation, the drag force was much larger as it is dependent on the square of the velocity, as well as the distance traveled by the ball was significantly larger due to the heightened average velocity across the entire interval. So in conclusion, in this lab, we looked at the physics underlying the motion of a falling object and created a Python model to closely simulate this motion and determine the value of the drag constant for the beach ball. Terminal velocity was not observed in our experiment or any of our models, as in all cases the object continued to increase in velocity as time passed, thus was still accelerating due to the magnitude of the force of gravity being larger than that of the drag force.